Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing an important topic which is transition metal sigma alkyl complexes over the last few lectures and have been looking at it from the methods that are available for their preparations. We have also looked at the reactivity, the stability of these compounds. In particular, in the last lecture, we have looked at different strategies that are available to stabilize these transition metal sigma alkyl complexes, which otherwise are very reactive compounds. And all of these strategies that we have encountered are focused towards one particular decomposition reaction, which is beta elimination. And what we had seen that all of these strategies are put in place to suppress beta eliminations in transition metal sigma alkyl complexes, and if done successfully, they impart reasonable stability to these organometallic compounds. So, in the pretext of beta elimination, we had seen that there are primarily three approaches towards inhibiting it. The first one is sort of the application of Brett's rule. The second one applies towards ligand which does not have beta hydrogen, so that beta hydrogen elimination does not undergo, and last one is the one that focuses on the metal center by making the metal center coordinatively saturated. As a result, beta hydrogen elimination is inhibited. Now, with that in mind, we were in the last class we were looking at the reasons for decomposition of titanium tetramethyl. Titanium tetramethyl is a highly reactive compound that has a decomposition temperature of around minus 40 degrees centigrade, and this compound is both coordinatively unsaturated as well as electronically unsaturated. As well as electronically unsaturated. Coordinatively unsaturated means that it has a coordination number of 4. So, still most of the transition metal exhibit coordination number as high up to 6. So, in that from that pretext it is still coordinatively unsaturated, and it also is electronically unsaturated as it has total valence electrons of 8. So, this is highly electronically unsaturated as it has 8 valence electron as opposed to the inner transition metal complexes which obey 18 valence electron rule. And because of this extensive unsaturation, both coordinative as well as electronic, this titanium tetramethyl decompose by a bimolecular pathway. That involves the interaction of titanium with the titanium methyl bond of a neighboring molecule. This weakens the titanium methyl bond, as these are 3 centered 2 electron non classical bonds, resulting in decomposition of this titanium tetramethyl moiety. Now, while analyzing this, one can conceive that if somehow the coordinative saturation along titanium, if it is increased either by coordination, increased coordination, or through sterics, then one should be able to attain a more stable titanium complex. For example, if one goes to titanium methyl triethoxide, where you have one alkyl attached to titanium, for example, then one sees that because of this O ethoxy, which is slightly more bigger than the methyl moiety, and also the oxygen has a lone pair in it, which are stereogenic in nature, then this bimolecular pathway can sort of be more conspicuous. Is more conspicuous or is visible in this complex, as this complex exclusively exists as a dimer of the type shown. So, this is a exclusively dimeric molecule, and this fully supports or gives evidence to the bimolecular pathway as observed in the titanium tetramethyl complex. The difference being, this is a 3C 2E bond, whereas in this case there are two classical 2C 2E bonds between titanium and oxygen. Otherwise, this bears a testimony to the fact that titanium is both electronically as well as coordinatively unsaturated in this titanium tetramethyl complex, and that it undergoes the decomposition pathway using this bimolecular mechanism. Now, if one improves or increases the steric bond of this ethoxide in titanium to something which is more bulkier, for example, say isopropoxide, even this dimer becomes a monomer. So, that brings us to a very important compound, which is titanium methyl triisopropoxide. This is mostly monomer. Now, for this kind of complexes R, Ti, X3 type complexes, the pi donor strength increases along X being chloride less than OR less than NR2. Another interesting observation to be made over here, that apart from the bulk of the isopropyl moieties that make this complex monomer, there is also some kind of pi interaction occurring between the oxygen lone pair and the empty d orbital of titanium. And oxygen lone pair, and hence the importance of pi donor strength increases, and it turns out that the pi donor strength increases from X being a halide to alkoxide to a dialkyl amine moiety. Now, we come to this important observation of the fact then that when all the criteria for suppressing beta elimination are realized, the three criteria being that formation of the olefin is inhibited from beta elimination owing to the olefin being energetically unfavorable. The second criteria is that the ligand would not have any beta hydrogens on the beta carbon, so that the beta hydrogen elimination anyway will be inhibited. And lastly, if the metal central metal atom in the organometallic compound is coordinatively saturated, then it will not participate in any kind of beta elimination process. Now, if one were to design a molecule where all of the three criteria are fulfilled, then that molecule is expected to be very stable. When all criteria that we have discussed for suppressing beta elimination are fulfilled, then very stable complex is obtained. For example, this particular chromium complex which has a dimethyl arsine and a aryl group with CH2, three of this ligand bound to the metal center of this type, what results is a very extremely stable compound that is stable up to 350 degrees centigrade. So, this is extremely stable compound, and what we see that all the criteria of beta elimination have been inhibited. For example, there is no beta hydrogens, that both the beta positions are blocked. Secondly, that these will not give a olefin that would be energetically favorable, and lastly the metal being 6 coordinated with arsine and 2 of the dimethyl moieties and a phenyl ring is extremely coordinatively saturated. So, no way can the metal center chromium participate in any kind of beta hydrogen elimination. So, the formation of these compounds testifies that the approaches which have been undertaken towards inhibiting beta elimination is a successful one. As a result, one can obtain organometallic compound that is extremely stable. Also, this example negates the fact or belief that organometallic compounds are thermodynamically unstable, but it turns out that the thermodynamic stability is not much an issue for organometallic compound, whereas kinetic reactivity resulting to its so called observed instability is what is the primary reason for their extremely high reactive nature, and that can be suppressed by obtaining a proper understanding of their decomposition pathway. For example, transition metal sigma bonds can occur in classical Werner type kinetically inert complexes. So, these being kinetically inert, as they are both kinetically as well as coordinatively saturated. For example, these are mainly seen for chromium 3 D3 systems, cobalt 3 D6 systems, rhodium 3 D6 systems. For example, for rhodium pentamine, two plus, where 5 ammonia and 1 ethyl group is bound to the rhodium. So, rhodium has 5 ammonia and the ethyl group has the beta hydrogen. However, this compound is kinetically inert, as the metal center is both coordinatively and electronically saturated. So, coordinatively saturated means it has a coordination number of 6, and electronically saturated meaning that it is a 18 valence electron complex. The 18 comes from 10 plus 10 from the amine plus 1 11, and rhodium in a neutral method is 9 11 plus 9 20, and there is 2 charge. So, this is the 18 valence electron complex. So, this complex, as we saw, being both electronically and coordinatively saturated, is because of this saturation, this complex is overall kinetically inert despite having a ethyl moiety which has beta hydrogen. So, what we saw that if the third criteria for elimination is satisfied properly, then the ethyl moiety, despite having a beta hydrogen, cannot eliminate, and the compound becomes kinetically inert. This is a very interesting example. Another example is this transition metal alkyl bond, when bound to main group elements as ligands, sometimes are also stable, and the example is this class of compounds called organorhenium oxides. So, in organouranium oxides, main group elements act as ligand in addition to or alongside sigma alkyl ligands. To illustrate this, like to give the following examples. Methyl rhenium trioxide or methyl rhenium oxo bis peroxide or dioxorhenium trimethyl These are a class of compounds where there is a rhenium alkyl moiety bound to heavier atoms. These compounds has tremendous application in various catalytic reactions, which we will take up in the following class. In this class, I summarize that we have looked into the kinetically inert nature of transition metal sigma alkyl complexes, the reason behind that, and also how to make extremely stable transition metal sigma alkyl complexes by suppression of various beta hydrogen elimination pathways, and if all of the strategies are put in place in a single molecule, if all of them is realized all together, then extremely stable or transition metal sigma alkyl complexes may be synthesized. And also we have seen that if a metal center is coordinatively as well as electronically saturated, then metal sigma alkyl groups, despite having beta hydrogens, they would not eliminate and the compound would be more stable. And with this, we look forward to this important class of compounds in the next lecture called organorhenium oxides, which has very good applications in chemical catalysis and oxidation reactions, and that will be the subject of the topic for the next lecture. Thank you.